So in the rest of this lecture, we are going to learn how to actually construct this tree to make sure it satisfies the properties that we have listed earlier. Okay, so we're going to see how to do insertion, and then after that how to do deletion in B trees. Now insertion in a B tree is done in such a way that it ensures the following. Its height remains balanced. Its leaves are all at the same level. And as we specified in its property, each node except the root is at least half full. That is, it has a minimum of ceiling of m/2 minus 1 keys. Each node except the root must have this number of keys. Okay, now a node of a B tree of order m. Okay, so we define a term here because we're going to need it when we come to the insertion. And overflow, what does it mean, overflow? A node of a B tree of order m is said to overflow if after insertion it will contain m keys. Remember, the maximum number of keys allowed is m-1. So if your node will contain m keys after our insertion, then definitely it overflows. Okay, so with this definition in mind, here are the two insertion cases that we have. Insertion case number 1, the leaf in which the insertion is to be done does not overflow. By the way, the insertion has to be done on a leaf node. It's similar to insertion on BST, if you remember. You have to keep going down, left or right, until you reach an empty node, then you insert. Now here we don't insert an empty node. Rather, we find a leaf node, and then we do the insertion on that leaf node. So this is where these two cases arise. The leaf node that you're going to insert into, you may be lucky that it will not underflow. So in that case, just insert the keys. There is nothing to do, just put the key there. Okay, so this is case number 1, which is the easy one. The leaf in which the insertion is done does not overflow. But what if the leaf on which you're going to do the insertion is already full? Okay, so the leaf overflows. Now here, it depends, what you're going to do depends on whether the m is odd or even. So you have case 2a here, where the order of the tree is even, and case 2b, where the order of the tree is odd. Okay, I will show you both ways how to do it. Basically, you're going to split the node into 2 because it cannot have more than m-1 keys. So you're going to split it into 2 and create a parent for this 2, and that the middle node will go up. So the issue is, if it is even, the middle node is not clear. What is the even? What is the middle node? We're going to see that. Okay, so those are the two cases we're going to study. How to do insertion in a case where the leaf node does not overflow, and then how to do the insertion where the leaf node will overflow. Okay, so let's start with case number 1, which is easy, where the leaf does not overflow. So suppose you have this B tree. We are trying to create a B tree of order 5. Okay, this has to be mentioned. It should be clear what is the order. Okay, suppose we want to insert key 7 into this tree. So as we do in BST, we ask, is 7 less than 12 or greater than 12? Obviously it is less. So we're going to go to this leaf node. This leaf node given that this is a B tree of order 5, I should have written it somewhere, which is not written, it's actually order 5. You can observe that from the keys that each node can have 1, 2, 3, 4. So the order is 5. 1, 2, 3, 4, 5. All right. Now the leaf node here has room, has 2 cells that we can put our, so we can add our 7 there. However, to add the 7, we must make sure the elements are in ascending order or increasing order. So actually the 7 is going to be placed between 5 and 8. So we have to shift 8 to the right to create a room for 7. And that's what you will see here. See, after the insertion, this is what you have. Okay, so if the leaf has room, it doesn't overflow, then just go ahead and insert the key in the correct place in that node. As simple as that. Okay, now let's take a case where the node will overflow. Okay, so here it says insertion case 2a, the leaf overflows and the order M is odd. Okay, so this is usually the easier of the two different cases in case 2. So this is our B tree. We want to insert key 6. Obviously 6 is less than 12. But the leaf node that we have here is already full. Okay, so you will say, okay, if I were to put the 6, where is it going to be? It's going to be somewhere here in between 5 and 7. Okay, so you say, okay, I'm going to split this node, 2 elements on the left, so the 2 and 5, 2 elements on the right, so the 7 and 8. The 6 that I'm going to put, I will now instead put it in there in the parent. Okay, so you're gonna create another element here in the parent. This is actually how the nodes, other than the leaves, how they get more elements, by splitting the leaf node if it is getting full or if it will overflow, and moving the middle element to the top. So basically this is the situation so far. So you split this node into 2. So we have one node with 2, 5, another node with 7, 8, and you try to move the middle element to the parent. Okay, so when you come to the parent, you're going to shift the 12 here, and then you put the 6 here, and then there's going to be a link between to the right of 6, the right link will come to this node, and to the left of 6 will come here, exactly as you are seeing it here. So this is the final result we're going to have. After pushing 6, or after inserting 6, this is what we have. You see the parent now has 2 children, 2 keys. Okay, the parent node, the root node, has 2 keys. The 12 has not changed if you look carefully. To its right, we still have 13, 15. To its left, however, we now have only 7, 8. Okay, that 7, 8 is also to the right of 6. Okay, to the left of 6, we will have 2, 5. This is basically how we insert a key where the leaf overflows. We split the node and push the middle up. Now here it just happened that the key we are inserting is the middle. What if it is not 6 we are inserting, it is 9, for example? Okay, so in that case 9 actually will be after 8, right? So when we split, it is actually the 7 that is the middle. So it is the one that moves up to join the parent node. So that on the right here we will have 8, 9. On the left here we have 2, 7. Okay, so it's not necessarily that the key that you are inserting is the one to move to the parent. No, just the middle one. The middle one, if you split the node, is the one that will move to the parent. Okay, this is another example, this time using letters, and here the B tree is of order 3. So order 3, you have to be careful. The maximum number of keys is 2. Okay, the minimum in this case doesn't matter between root and the other node, because ceiling of 3/2 is actually 2. So all other nodes will also have maximum 2 subtrees. Maximum 3 subtrees, minimum 2 subtrees, and maximum 2 keys and minimum 1. All right. Okay. So let us say we want to insert S in this tree. We want to insert S. Now S, if you know your A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S. So P, you can see S is after P, Q, R, S. Actually, S is going to be here. Okay, after the R. Now, unfortunately, the leaf node here is already full. So you have to try and split it, and we'll have one node on the left, one node on the right, and the middle R will try to go up. This is what we are having here, as you can see. We splitted the node. The S is on the right, the Q is on the left, the R is trying to join the parent. However, when you come to the parent, it is also full. It has 2 keys. 2 is the maximum you can have, maximum keys you can have in a B tree of order 3. So what do? We again have to split. We will have R on the left. Okay, so that R will actually be the parent for your Q and S, as you can see here. It will have Q on the left and S on the right. It will have N on the left, and P will try to join the parent. But the parent is also full. So what do? Again, you have to split. You will have H on one side, and the P that just came up will be the one on the left. So it will be the parent of the R and the N. And the middle L will try to go up. So actually, we are creating a new root with only L, at the very top here. This is the tree that you're going to get after this insertion. In other words, what this shows is that insertion can actually result in increasing the height of the tree and creating an entirely new root, because this splitting pushing the middle up can propagate until the root, and if the root happen to be full, then we're going to split it also and create a new root. This is what happened in this case. Okay, so this is insertion where the node will overflow and the order is odd. We still have not seen the case where the order is even. This is what we shall see here in this example. So insertion case 2b, where the order M is even. So suppose we have this segment of a B tree of order 4. So 4 is even, and we are trying to insert 102. All right, 102 obviously is more than 87 and less than 140. So it's going to try and follow this branch, and when we come here, this is the node that is leaf that we will find, but it is already full, because for order 4 The maximum keys is 3. This is already maximum. Okay, so you ask yourself, where is 102 going to fit among these 3 numbers? It's going to fit between 100 and 106. But it's going to overflow, so we have to split it. And now here is where the problem comes. Because when we split, the total is 4. So how are we going to split it? Okay, it's not going to be like the odd where we will have 2 and 2 and then 1 in the middle. Here we have to have either 2 on the left, 1 on the right, and then the middle, or 2 on the right. Okay, so in that case we're going to have the 102 and the 106 on the right. The middle will be the 100, and then only 90 on the left. So this is why in a situation where the order is even, we actually have 2 options. Either we do it left bias. So left bias means the left subtree, or the left half after you split, will have more elements than the right. So if you do that, in this case, the 90 and 100 will remain on the left. The 102 will move up to join the parent. And that is what you're going to have after the insertion. So you can see 90 and 100 are here. In the middle, 102 has moved up to join the parent. And on the right here, you have 106. You could also choose to do it right bias. So right bias means it is 102 and 106 that will form the right. The middle 100 will move to join the parent, and this is what you're gonna get in this case. So the answer is not unique in this case. It depends on whether you are doing it left bias or right bias. This is why actually in our exams we normally try not to give questions that involve even number m. Okay, it's still good to know how to do it, but you can be guaranteed that in an exam you will not be asked to do a question that involves an even number. If you are given, then definitely you will be told which of these 2 options you should follow, whether left bias or right bias. But most likely you will not be given a question that involves an even number. So this is basically how to do insertion. What we are going to do next to make sure this idea is really understood, we are going to take one big example and try to follow it through to construct a complete B tree from the beginning, from the scratch, to insert in these numbers. So this is the example. It said insert the following keys into an initially empty B tree of order 5. Okay, and these are the numbers 8, 14, 2, and so on. So we're going to do it step by step. Obviously, the first 4 numbers can fit into our initial leaf node. So nothing to do other than making sure they are in the correct order. So we put 8. Then when 14 comes, we see that we have to put it to the right of 8. When 2 comes, we have to put it to the left. And when 15 comes, we have to put it all the way to the right. So all the while we are dealing with one leaf node. But now the leaf node is full. So if we try to insert 3, this node will overflow. Okay, so you'll ask yourself, where will 3 fit in? 3 will fit in just after 2, and therefore we're going to split the node. On the left, we're going to have 2, 3. On the right, we're going to have 4, 15. And the middle will now form a new root node. Therefore, after inserting 3, this is what you're going to get. After inserting 3, we now have a new root 8. To the left is 2, 3. To the right is 4, 15. Okay, so let's continue. Inserting 1 is easy. It's going to fit, of course, 1 is less than 8. That's why we are going to come to this node. And it's going to be just before 2 and 3. We still have one more room. After inserting 16 here, so 16 will go to the right and it will fit here. Again, no issue. Okay. When you put 6 is going to be in this node, and at that point this node will be full because it will have 1, 2, 3, and 6. Okay, right. So when you attempt to put 5, you're going to have a problem. Okay, so let us see what we are talking about. When you try to insert 5, okay, given that this node is already full, it already has 1, 2, 3, and 6. Now, if you try to put 5, the node will overflow. The question is, which one is the middle? Okay, obviously it is the 3 that is the middle. On the left, you're going to have 1, 2, and on the right, you have the 5 and 6. The middle 3 will move to join the parent. So this is what I'm showing you here, the result after inserting 5. Okay, you can see the 3 has moved to join the parent. To its right we have 5, 6. To its left we have 1, 2. This is the state so far. 27 will fit here, no issue. The node, however, is full. So when you attempt to put 37, it will overflow. So again, you have to split. This time, the 16 is going to be the middle one. On the left, you're going to have 14, 15. On the right, you're going to have the 27 and the 35, the 37. 27, 37 will be on the right. The 16 will move to join the parent. Okay, so this is what you're going to have after inserting until 37. Okay, so the parent is gradually getting full as well. Yeah, so this is what you have after inserting 37. 18 will fit in this node because it's bigger than 16. Okay, so it will shift to 27 and 37 and it will fit here at the beginning. 25 will also try to go to the same node. So we're going to have 18, 25, 27, 37. And now the node is full. Okay, 7 will fit in this node exactly here. 13 is bigger than 8 and less than 16. So it's going to fit here. So far no issue. It will fit in this node. Okay. The 20 is the one that will create problem actually, because this node 20 is going to try to fit here, but this node is already full. If you recall, we had 18, 25, 27, and 37. So if you try to put 20, the node will be full or will overflow. The question is, which one is the middle? The middle is going to be 25. On the left of it, we will have 18 and 20. Okay. Then the 25 will try to move and join the parent. And on the right, we're going to have 27, 37. So this is what you have after all of those insertions. After inserting 18, 25, 7, 13, and 20, this is what you will have. Okay. So you only need to draw a new tree actually if a splitting occurs. If a splitting occurs, you have to draw a new tree and show the result. Otherwise, just keep shifting and putting the elements. Okay. So this is the state we have after inserting 20. Now our root is full. If there is any splitting again, we have to split even further, and we're going to create a new parent. Okay, so 22 bigger than 16 but less than 25, so it will fit here, no issue. Also 23 will fit there, no issue. But if you try to insert 24 also in this node, it will overflow. So you have to split. Okay, the middle is going to be 22. To its right, we will have 23, 24. So the middle will try to come here, but this node will overflow. Okay, will overflow with the 22 here. So we have to split it. If you split it, we will have 3 and 8 on the left, the 22 and 25 on the right, and the 16 will form the new root. We'll move and create a new root, and it will be along there. So this is the final result you're going to get after this insertion. See, we have 16 here as the new root. To its left, we have 3, 8. To its right, we have 22 and 25, and so on and so forth. I hope this gives you an idea how to do insertion in a B tree. Okay, the final part that we're going to study about B trees is deletion. Like insertion, deletion must be done on a leaf node. You will be surprised by this, because what if the key you are deleting is not on a leaf node? It says here, if the key to be deleted is not in a leaf, you have to swap it either with its successor or predecessor. And the thing is that the predecessor or successor, they are always on a leaf node. So you have to swap it with the predecessor or successor, then try to delete it at its new position in the successor or predecessor. So the deletion must also be on a leaf node, as we shall see. Deletion must be done such that the leaf node from which you are deleting does not underflow. So in case of insertion, our worry is overflow. A node should not have more than what it can take. Here it is the reverse. A node should not have less than the minimum allowed. As we know in B3, a node cannot have less than ceiling of m/2 minus 1 keys. Unless if it is a root, then yes, it can have 1 key. But all other nodes must have a ceiling of m/2 minus 1 keys at the minimum. So because of this, we have so a non-root node of a B3 of order m is said to underflow if after deletion it will contain ceiling of m/2 minus 2 keys. This is underflow condition because the minimum is ceiling of m/2 minus 1. All right. Now there are 3 deletion cases. For insertion, there are only 2 cases: whether the node doesn't overflow or whether the node overflows. But here there are 3 cases. Case number 1, the leaf does not underflow. So if this is the case, just delete, no issue. 2, the leaf underflows and the adjacent right or left sibling has more than the minimum. This is of course more than the minimum. Remember, the minimum is this number minus 1. Ceiling of m/2 minus 1 is the minimum. So the right or the left has more than the minimum, and you can therefore borrow from that left or right to solve the underflow problem. Again, we shall see what this means with an example. The final case is the most difficult one, where the leaf will underflow and none of its adjacent sibling has more than the minimum. So each one has exactly the minimum, so we cannot borrow from the siblings. So in that case, we have to do what is called margin. We will see that with example. So those are the 3 cases of deletion, and we're going to take them using examples, starting with case 1. Deletion case 1, where the delete node does not underflow. This is the easiest case. So suppose you have a B tree of order 4 here, and we wish to delete 140. Now notice 140 is not on a leaf node. Okay, so this example is given specifically to show you what to do if the node being deleted is not on a leaf, because deletion must be done on a leaf. So what you do here, before you attempt to delete 140, you're going to swap it with either its successor or predecessor. What is the successor of 140? Actually is the leftmost node, rather the leftmost key in this node, which is 152. So what you do is you swap. 152 goes up and 140 comes down, and then you try to delete the 140 from this node. Deleting 140 from this node will not create an underflow, because in a B tree of order 4, the ceiling of 4/2 is actually 2, and we can have 2 minus 1. We can even have 1 key, so there is no issue. Okay, so actually even if we use the predecessor, it will still be fine, because we can delete and still have 1 key left. But it is more appropriate here to do the deletion with the successor, because the successor node has more keys. All right, so this is what we will have after that deletion. See, the 152 has been swapped. It goes here. 140 came here and immediately deleted. So we are left with 186, 194. And this is the deletion where the node to be deleted, the node in which the deletion occurs doesn't underflow. All right. Case number 2A. So the leaf underflows, but the adjacent right sibling has at least the ceiling of m/2 keys. Deletion case 2A says the leaf underflows, but the adjacent right sibling has more than the minimum. This is more than the minimum. Remember, the minimum number of keys is ceiling of m/2 minus 1. So in that case, what you do, actually you do a kind of rotation. This right sibling, we're going to borrow one element from it, the leftmost element, and we're going to do the rotation with it through the parent of the two siblings. So this is the node we are deleting from. It's going to underflow. So we do a kind of rotation. We borrow one from each sibling. This time, in this case, the right sibling. So y will be removed from this node. It will go and replace the x, and x will come down to join the new node, so that even after we do the deletion, it will still maintain the minimum. This is the idea. Let's see the real example. Suppose this is the situation you have in a B tree of order 5. Remember, for order 5, the minimum number of keys is 2. All right. So suppose we wish to delete 113. Okay, 113 is already on a leaf node, so there is no swapping needed. Just try to delete the 113. However, deleting the 113 in this case will make this node to underflow, because it will have only 1 key left. So this cannot be done directly as in case 1. However, if you look at its right sibling means they share a parent. These two nodes, they share 120 as the parent, as their common parent. So what you do is you borrow this 128, okay, the element to the leftmost in the right sibling, borrow it so that this node will be left with only 135 and 142. But you don't borrow it directly to the node, no. You make it to go and replace the parent. So the parent will now be 128, and this current parent will come down to join this node that we are deleting from. So it will have 3 keys, including the one that we are deleting, so that after the deletion, it will still have the minimum number of keys, which is 2. Okay, so basically this is what you will end up with. So that node will now be having 90 plus the 120, which was the original parent. Okay, but the original parent has now been replaced with 128. So this is the idea. You could have similar situation if it is the left sibling that has more elements. You can also borrow from the left sibling. Okay, so this is what we call case number 2b. The leaf underflows, but the adjacent left sibling has at least ceiling of m over 2 keys, so it has more than the minimum. Okay, so in that case you do very similar situation. We're going to borrow from the left sibling. This is the node that will underflow, so we're going to take the rightmost element this time because it is the one that is predecessor to the parent. So the predecessor to the parent will go and replace the parent, and the parent will join the node being deleted so that it will not underflow. So let's see a real example. Suppose we wish to delete 135 in this B3 of order 5. So 135 will make this node to underflow given that the tree is of order 5. One key is not allowed. It has to be at least 2 keys. But its immediate left sibling has more than the minimum. It has 3. The minimum is 2. So we can borrow this last element. It is the predecessor to 120, so it will go and join the 120, which is the parent. 120 will come and join this node. So we have 120, 126 after deleting the 135. And this is what you get as the final answer. So this is basically case number 2. The node will underflow, but you can borrow from either the left sibling or the right sibling. In case you have both options, because it's possible that the node you are deleting is somewhere in the middle of a left and right sibling, and both the right and left sibling, they have more than the minimum. Then now you have two options. Either you borrow from the left or you borrow from the right. Now usually the question will ask you to do it in a specific way. It will say if you have two options, do it with the left sibling or with the right sibling. So you have to be able to know both. You have to know how to do it in both ways. Let's go to case number 3 now. So case number 3, the leaf underflows and each adjacent sibling has exactly the minimum. This is the minimum number of keys that you can have in a B3 node. So what do you do in that case? In that case, you have to do what is called margin. Okay, so this is the situation. This node, if you delete from it, it will underflow. The right sibling has exactly the minimum number of keys, and the left sibling has exactly the minimum number of keys. So in this case, you have no option but to do what is called margin. Okay, you have actually two options for margin. Either you merge the node that will underflow with its right sibling along with their common parent. So the common parent will come down actually. So all of this will form one node, as you can see here. Okay, so we're left with only V and the rest of the keys in the parent. The X has come down. It is now in the middle of the merge node. To the left of X, we will have all the keys in the left, and to the right, we will have all the keys in the right. Okay, this is one way of doing it. Say merge node sibling, merge the node sibling and the separating key X, or the parent key X. Okay, we could actually do it also with the left. So we could merge this with this along with V. Okay, so we could do the margin here. This is what this note will say. It's a note. The margin could also be done using the left sibling instead. Okay, now let's read this note. It says if the parent of the merge node underflows, because you see you're removing one element from the parent. So if it also underflows, then the merging process will propagate upwards. Okay, so, but of course, before you try to merge, you have to see, can you borrow from the sibling of the parent to solve the problem? If you can borrow, borrowing is the first step. But if you cannot, again, you have to do another margin, and this margin can propagate upwards. In the limit, the root with only one key will be deleted, and the height of the tree will decrease. So just like insertion can increase the height of the tree, deletion may result through this merging process in reducing the height of the tree. And we're going to see this as an example. Okay, so let's take the example. Suppose we have this tree, which is order 5. So minimum keys is 2, cannot go less than 2. All these nodes are in their minimal state. And suppose you want to delete 142. Okay, obviously this node will underflow after the deletion, so that's not acceptable. Can you borrow from the right sibling? No, it is in the minimal state. It has only serial over 2 minus 1 keys, so you cannot borrow from it. Can you borrow from the left sibling? Again, no. It has the minimum number of keys. So you have to merge, therefore. This is the only option. And in merging, as I said, you have two options. You can merge this node, which will underflow, along with the left sibling, along with the common parent 395. So they will form one merge node. Or you could do it with the right sibling. So you could merge this with the right along with the common parent 430. Okay, now one thing to observe is that when you do the merging, the new node that you're going to form will be in its maximum state. Okay, this is always the case. So make sure when you merge, you have, in this case, because it's order 5, the merge node will have 4 keys, which is the maximum. So this is the situation if we do the merging with the right. As you can see, the merge node has the remaining element after deleting 412, so we have 406, the common parent 430, and then the two elements from the right, 451, 472. Okay, notice the parent, in this case we are lucky, it still has the minimum, so no more margin is needed. The margin will stop here. But suppose after the margin, the parent reduced to 1, then you have to solve that problem. First, by attempting to see if it has a sibling that you can borrow from, or in the worst case, you have to again merge. Okay. Of course, if it is the root is allowed to have 1 key, so nothing to do. Okay, but if it is not the root node, then you have to solve the problem as well. Okay, so this is our first example. So that's what we are saying here. The parent of the merge node does not underflow. So the merging process does not propagate upward in this case. It stops here. Okay, another example. Again, B3 of order 5, but this time with letters. Let us say we want to delete D. Okay, so you want to delete D. Obviously, it will make this not to underflow, and you cannot borrow from the left or from the right. Again, I emphasize, before you attempt merging, you have to always check, can you borrow from the siblings? Only if you cannot borrow from the siblings, then you merge. Okay, so in this case, both the two siblings are in their minimal state, so we cannot borrow, so we have to merge. Okay, we have chosen this time to merge with the left, so delete the key D and merge this together. So the elements in the left plus the common parent C plus E will form one complete full node, A, B, C, E. But this has created a problem because the parent here has only one key. And we know in a B tree of order 5, only the root is allowed to have one key. Okay? So at this point, what you should attempt to do is to see the sibling of this F, does it have more than the minimum? Unfortunately, no. It has only the minimum 2 keys. So again, you have to merge. This time you merge this tree. The node that has underflown its right sibling in this case, along with their common parent. And therefore, the height of the tree actually is going to reduce, and you will have this situation. So after merging, this will form one node, FJMT, and as you can see, the height has now reduced to just 2. Okay, and you adjust the arrows accordingly. Okay, this is what you have after the merging process. And to the left of M is still KL, as you can see here. To the right of J is still KL. Okay, and to the left of J is GI. So you should maintain the same order as this, just that you are bringing the J down to join and form one node. Okay, and again, if you count, I emphasize this at the beginning, the number of subtrees must always be exactly one more than the number of keys. So since this merge node is full, it has 4 keys, the subtrees must be 5. 1, 2, 3, 4, 5. Okay, this is always the case. Let's take a case where the node will underflow, and the parent after doing merging, the parent will underflow, but we can borrow. So in that case, we don't merge right away, we just borrow. Okay, so suppose this is we want to delete the key 40 in this B tree of order 3. So order 3, the minimum key you can have is 1. So meaning underflow is if you have an empty node, that is underflow. Okay, so we want to delete 40. Obviously 40 will underflow because it will have empty. All right, can you borrow from the sibling? No, you cannot. So you have to merge this 3 into one node. Of course, after deleting the 40, they will now become 2. But then you're going to have a problem here in the parent. It will now become empty. Okay, so after merging this 2 and deleting the 40, this is what you have. But the parent has now underflown. So this is the point I was trying to stress. When a parent underflows, don't try to merge immediately. Try to see the sibling. In this case, the left sibling. Can you borrow from it? Obviously, you can in this case because the minimum is 1 in a B tree of order 3. Okay, and this guy has 2 keys, so we can borrow 1. So you borrow through the parent. Yani 8 will go up to form the new parent, and 12 will come down to join this node. But you have to make the necessary adjustment because now this 10 will have to go with its parent. So, and the parent has moved to become the parent, to become the root. So this is what you will end up with after you rotate the 8. So you see 10, which is to the right of 8. Even after 8 comes here, it will still be to its right. Okay, so actually it's going to be to the left of the 12 that you're going to rotate here. So this is the final result you get after that process. So when a node underflows, don't just merge. See if you can borrow. And if you borrow, in this case, this is what you're going to have. I hope this is clear. Now, as we did with this insertion, we're going to take a sequence of numbers just to show you the process more clearly. What steps do you need to follow if you need to delete a sequence of numbers? So this is our tree of order 5, B3 of order 5. We want to delete the keys 6, 7, 8, 16 in this order from this B3. What is the process? So it will show you all the different cases where there is nothing to do, where we only need to do a rotation, and where we have to do a margin. Okay, so the first case is really very easy, deleting 6, because 6 is already on a leaf node, and the node has more than the minimum 2. Remember, for order 5, minimum is 2 keys. So we can delete the 6 directly, there is no issue. We will be left with 5, 7. Okay, this is deleting the 6. What about if you try to delete 7 now? Obviously, this node will underflow. But luckily, the right ceiling has more than the minimum. So you can borrow. You can borrow the leftmost one. So 13 will come and replace the parent here. And the parent 8 will come and join this node. And here we will be left with 5, 8. And 7, of course, will be deleted. So this is what you have after deleting 7. I just reproduce the figure there. So after deleting 7, 13 will go up to be the new parent, and 8 will come down to join the delete node, and 7 will of course be deleted. Okay, next we want to delete 8. 8 on the same node instantly will create an underflow, but this time you have no other way of deleting. You cannot borrow. You cannot borrow from the right, you cannot borrow from the left. So you have to merge. Okay, you have two options for merging. In this case, you can merge with the right. So 13, 5, 8, and 14, 15 will come and form one node, of course, with the 8 deleted. Or this node and 3 and the left. So 1, 2, 3, 5. The 8 will be deleted. Okay, let's see the option we followed. This is the situation, and this is the result. Okay, so we opted to merge with the right. So we will have 5, 13, 14, 15. But that has created a problem here. This node has only one key. Only the root is allowed to have one key. So the next question you should ask yourself is, can we borrow from the right sibling to solve this problem? Unfortunately, you cannot, because the right sibling also has only 2 keys. So the only solution here is to actually merge. So you're going to merge this node. We're going to have, after deleting the, you're going to have 3, 16, 25, 22, 25 as one node, which will now be the root. So actually the height of the tree will reduce. This is what you're going to have after the deletion of the 8. So the root now has 3, 16, 22, and 25. Okay, and the subtrees are as before. The last part is to delete 16. Obviously 16 is not on a leaf node. Okay, so as we said, you have to swap it with either its successor or predecessor 15, each of which is on a leaf node, successor 18 or predecessor 15. Now in this case, it doesn't make sense to swap with the successor, because after you swap, you're still going to delete and we will be left with one key, and that is not allowed. So you have to do another process to solve that problem. But the node containing the predecessor is a full node, so we can borrow from it without creating any problem. So what you do is swap 16 with its predecessor. So 15 will go up, 16 will come down and immediately delete it, and without creating any problem. So we'll be left here with 3 out of 5, 13 and 14 as the resulting node after the deletion. So this is what you have: 5, 13, 14, and 15 has moved up to swap with the 16 being deleted. This is basically the example. I hope it has given you an idea how to do deletion in a B tree. The last part of the lecture is to briefly talk about another balanced multi-way tree, which is called B-star trees. B-star tree is even more efficient than B trees, but I will not go into detail about its deletion and insertion, but just to tell you something about it and to give you two examples. So in a B-star tree, all nodes except the root are required to be at least 2/3 full. You see, in B tree, it should be half full. So here the requirement is 2/3 full. So this is even more efficient than B tree. Okay, so it has to be at least 2/3 full, not just half full as in the case of B tree. Because of this, the frequency of node splitting is decreased, because you don't split when it is getting, we will see, because actually what will be done is you will rearrange the elements to make sure you don't just split anytime the node get full. We will see the example in a moment. So the frequency of node splitting is decreased by delaying a split, as we shall see in the next slide, and by splitting two nodes into 3, not just into 2. Okay, so when two siblings get full, then you break them into 3. Okay, so the average utilization of B star tree is 81%, which is much better than B tree, which is only 50%. Okay, let's see just a small example, and we want to insert 6. 6 is less than 16, so it's supposed to fit here, but that will make this not to overflow. If it were B3, we would just split and move the middle up. But no, in B star what we ask is, how about the right sibling? Can it take more elements? Yes, it can still take 3 more, you can see. So what we do is we rotate 2 more elements from the left sibling to the right sibling, so that 12 and 16 will join the right sibling and 10 will be the new root. Okay, so that will create 2 rooms in the left sibling, and with that we can now insert 6. Okay, so we delay the splitting until when even the siblings, the left and right, they have no rooms at all. Then we do the splitting. This is the idea. So this example shows how overflow in B star tree is circumvented or is avoided by redistributing keys between an overflowing node and its sibling. So this node is going to overflow if we insert 6. So we say, okay, before we attempt splitting it, can we redistribute the keys since this has more room? Okay, so we take 2 more keys there, and that leaves us with 2 room here, and then we can do the insertion successfully, leaving 1 more room for each of the 2 siblings. This is the idea. What about here? This is another example. What if the 2 nodes, both the 2 siblings are full? We cannot redistribute the keys, and we need to insert 4. Okay, so inserting 4 will be somewhere here before the 5. So what we do here, instead of splitting just 1 node, we actually split these 2 nodes into 3, creating some rooms for each of the node, so that next time we may be able to succeed in insertion without any problem. This is the idea. So if a node and its siblings are both full in a B star tree, a split occurs. A new node is created and the keys are distributed between the 3 nodes, as you can see here. So our interest is not for you to know how to do this insertion in B star trees, but just to have an idea about it. That B star tree is more efficient. It is usually 81% full. I mean, utilization is 2/3. We said 2/3 is about 81% compared to B trees. Okay, it is good enough if you know how to do insertion in B trees, not B star tree. Insertion and deletion in B tree you must know. B star tree, the only thing to know is what we have just said, that it is more efficient than B trees, because one, if there is a need for if there is an overflow, the splitting is delayed by redistributing the keys with siblings until when the siblings are all full. The second difference is that when you do the splitting, we don't split just a single node. We split the 2 siblings into 3. We split 2 full siblings into 3 sub-nodes, into 3 nodes, so that insertion can still be done after that splitting. Okay, this is all we need you to know about B star tree. We will not be asking you to do an insertion in a B star tree or a deletion. We didn't even talk about deletion here, but just to show you that there is an even more efficient tree than B trees, which is called B star trees, and this is how it is more efficient than B trees. This brings us to the end of our discussion on multi-way tree. Thank you very much.